Okay, so let's get started. Today we have two lectures back to back. So we will talk about protocols quite a lot. So I would say this is really fundamental basic knowledge for the course. So these are quite important, these lectures. Every lecture is important, but maybe this one is in particularly important, the material here. So please interrupt and ask questions as we go along, because it's better to take questions now than in week 7, right? Okay, so before we start, a few announcements. I've been nagging about this, but the project groups will be assigned this afternoon. You will receive an email about this and call for a kickoff meeting. Have you received this already? No? Okay. So you should come today. And if you have not received a message about this by, say, tomorrow morning, then something is wrong. And then you should email Shuaib, and because then probably he doesn't know that you exist, right? And that you need a project group. So please remember this. Let's get into things here. Networks. So what is a network? A network consists of many different pieces. It's quite common to draw a network like this cloud, and then something is connected to this cloud. So we have like two applications here connected to a cloud. But what's inside here are nodes. Nodes could be routers like these, or hosts, which are computers which are on the edge of the network, which are running some software, an application software here. These nodes are interconnected with links. And we will call, in general, we would call these at the end here, these computers. It could be a laptop, it could be a cell phone, or something which is at the edge of the network, a host. And I don't know exactly where the name host comes from, but I think it has to do with that it hosts application software. So it's running application software here. And this application software are used by humans or perhaps machines. And then these are interconnected with links, and inside here we have routers. And routers, the role of a router is to take an incoming message and send it out on the appropriate output link here. So it gets messages, stores and buffers them, and then put them out on the appropriate link. So there are many names for these boxes. And unfortunately, there is not a very crisp definition of what is a router and what is a switch and so forth. So names are sort of floating around a little bit. So I'm sorry for that, but that's just the way it is. So we'll try to keep things a little bit simplified in this course. So if I say something and then you Google it and you get a slightly different explanation for this, that could happen, right? But we will try to stick to the definitions that's in the book. But anyways, when I talk about an application, an app or a user, what I mean by that is something that uses the network. And typically this is a piece of software which is used by humans. It could be like Spotify, Skype, Amazon, or some other application that somehow uses the internet or a network. With a host, we mean something that runs software to support applications. I mean, some software that supports Spotify or so. It could be a cell phone, a laptop, a server, or something like that. Other names of hosts is end system, end node, source, sink, or edge device. So end system basically means that it's at the end of a communication path. Okay, either the start or the end of it. End node basically is the same as end system. Source means that it's something that generates data packets. Sink basically means something that consumes data packets. And edge device, I guess it's similar to an end system. Edge device, just to emphasize that this is at the edge of the network. It's not in the interior. In the interior, we have routers. We also have switches, hubs, nodes, or intermediate systems. And the purpose of these devices here, which are inside the network, is to relay messages between incoming and outgoing links. So such a thing would be here. And in this one, we have 5 ports, 5 incoming and outgoing links. So data comes in one link and then pops out in the other, possibly, right? So that's the role of this thing. Typical examples of this will be your Wi-Fi access point, ADSL modem, internet switch, Ethernet switch like one of these, and so forth. And then we have links, or we can also call them channels. And this is what connects nodes. So it could be cable, fibers, radio channels, and so forth. So I guess the physical manifestation of a link could be like a cable like this. Okay, so this is a link. But then you also have radio channels and so forth. Okay, questions? No, okay. So we will talk about these in detail, of course, some in more detail than others. So communication networks, they could be very, very complicated. Okay, very complicated machines consisting of many interacting pieces, both hardware and software. So we have these routers, switches, cables, radio channels, and protocols, and so forth. So one can, for sure, one can make an argument that the internet, as we know it, as we use it, perhaps is the greatest, biggest machine on Earth. Right? It's a hugely complicated piece of machinery, consisting of both hardware and software interacting in different ways, and it's so big that nobody really knows how big it is, right? We don't have a complete map of the internet, and it's all constantly changing. So when we have a big machine like this or a big problem, what is this? An approach to tackle this would be to when we want to design this or analyze this or do something engineering-wise with this big piece of machinery, is to divide it into smaller pieces. So divide and conquer is a classical approach for problem solving. One divides up the problems into sub-problems. We solve each sub-problem individually, and then we glue together the final solution. Okay. I mean, it's the engineering approach of modularity also. That if we want to perform a design, we split that design into smaller designs with very clearly specified interfaces between the designs. And then we put design teams on different parts of this machine. They do their job. And if the interfaces are well specified, when we glue them together, we have a solution for the big problem. Okay. So these are the steps. We want to split the overall problems into sub-problems in a smart way. We want to solve each sub-problem, and then we want to glue everything together to form a solution for the complete a solution to the complete solution, or the complete problem, of course. Okay, so the thing which I want to stress right now is the number 3 here. To do that with any success, it better be that the pieces fit together. Okay. So step number 3 requires very well-defined interfaces between the sub-problems. Because if we don't have good interfaces, team A builds something and team B builds something, and they don't fit. It's like pieces of a puzzle. They need to fit in order to form the puzzle. If they don't fit, we don't have a complete puzzle, a complete solution. Something that should be stressed also is that this approach of splitting up into sub-problems and then gluing it together, the overall solution is usually not optimal. whatever we mean by optimal. It could be optimal performance, or if it has a certain performance, this network, we could probably realize it with less resources if we did a complete holistic design, that we solved the whole problem from the beginning. But nevertheless, this modularity, that's to split this up into sub-problems, usually wins out in the long run. And the reason for this is that it's very difficult to maintain a monolithic design of something complicated. Because as soon as you make a little bit of a change in it, you have to verify that everything works in this big machine. So, and modularity, another thing from a commercial point of view, modularity is good, that because if you can define functions like a switch, you can have several vendors offering this solution, offering switches, and then you can buy the one that you like, which has the price performance trade-off that you like. So this is a Netgear device, but of course there are Cisco devices, there are many other vendors out there. Okay. So communication systems or communication networks is built on this fundamental idea of divide and conquer. And the division when it comes to communication systems or communication networks, the different pieces are called layers. So a layer, the overall problem then is split into these layers, and each layers are stacked on top of each other to form what's known as a protocol stack. So at the bottom we have layer number 1, then we have layer number 2 and so forth, and we can have different types of number of layers, 7 or 4 or whatnot. So the purpose of a layer is to provide services. Okay, so layer 2 here, for instance, layer 2 provides a service for layer 3. So layer 3 can use layer 2 in order to solve its tasks, right? And layer 2 uses the services of layer 1 to perform its tasks. So layer 1 interact with layer 2 interacts with layer 1 in order to provide the service to layer 3. Okay. So we provide services up in the stack and we use services down the stack. So provide and then use services. Okay. So that's how it's organized. So each layer in itself operates according to one or several protocols. So the functionality of a layer is determined by its protocol. And a set of layers with protocols is called the protocol stack. Okay. So we have layers. Inside the layers we have protocols. We provide services up and we use services down. All right. So this is super important, right, to keep this straight. Okay. Let's do an example before getting into, the structure and the theory around this. So we know that the internet is used for many things, including web browsing. So the web, what is it? Well, it's basically a distributed database. It consists of these HTML documents or other resources that are located at servers that are connected to the internet. So nobody knows how big the web is and where these servers are physically located, how many they are, and what they contain, and so forth. I mean, Google has a fairly good idea about many things, but far from everything. Now, a browser, your Chrome, Firefox, or Safari, or your favorite internet browser, is then used by users to locate and display these documents or resources. So how do we specify resources? Well, we specify them with something called the Uniform Resource Locator, or URL. I mean, you've seen this multiple times for sure. And it's a string of characters. It looks something like this. And it consists of three main parts. It's a protocol specification, or a method, and then a host specification, and then a path. So the protocol tells us how to access this resource. The host tells us where the server, which server has this resource. And here the path is basically a path to the resource on that server. So when a user clicks a link on a web page containing this URL, what happens? Well, the browser then figures out the IP address of the host, in this case www.chalmers.se, connects to this server, requests the file, receives the file, and then displays the output, interpret the content of this. Okay. Perhaps this is familiar to you, but this is what's going on. So let's look more in detail about this process. So the first thing to do, remember now we have four things here. We need to find the IP address, we need to connect, we need to request the file, and then we need to display the result. So the first thing to do is to find the server's IP address. That's step number one. So a user clicks on a link which requests some resource at this host, www.chalmers.se. Now the network does not understand where this server is located. This information here is basically for human consumption. It tells us that it's a web server, seems to belong to Chalmers, and it's located. It seems like to be a Swedish server. That's what we can decode from this as humans, right? But the network, for the network, this is not meaningful. The network needs an IP address in order to locate the server. So the internet name, which is, okay, so this is the internet name. And this is only useful, very useful for humans, but not so useful for the machine. So connect to the server, we need the IP address, or internet address, IP in this case. So then there is a protocol called the domain names system. This protocol is then used to look up the IP address to this. So if we have our web browser here, this is us, and the user then clicks on this link, www.chalmers.se, and then some path to some resource. What's going to happen then? Well, the first thing to happen is that the web browser uses DNS, this protocol, to query a DNS server. What is the IP address of this domain name or internet name? The DNS server then answers and say, okay, it's the IP address is 129.16.71.21. Okay, that's good. Now we have completed step number one. So do you see the logical flaw in this, perhaps, or something that I haven't mentioned? You nodding, or yeah? So the main problem here is, of course, so how this web browser needed to know the IP address of this server here, the www.chalmers.se, but how does it know the IP address of the DNS server? Well, it actually is configured from the beginning when it gets its IP address, and that's typically done with a protocol called DHCP. Now I forgot what the Dynamic Host Configuration Protocol, or I'm not sure what it means, but anyways, and we'll talk about that a little bit later. So we just assume now that once you have fired up your laptop, it gets its IP address, then it also gets the information about the IP address of the DNS server. Okay, so this is known. Okay, what is not known, however, is the IP address of www.chalmers.se, but this is now obtained through the DNS protocol by help of the DNS server. Any questions so far? Okay. Step number 2 is to connect to the server. So then the browser opens a connection to the server, and it does that using another protocol called Transmission Control Protocol, or TCP. Applications are addressed using port numbers. So we also need, in addition to the IP address, we also need to specify the port number. And the web browser software always listens to port 80. This we know. Okay, it's a so-called well-known port number. Okay, so people just decided that port 80 is where web browsers listen to, web servers and web browsers uses. Okay, the web server software. The web browser software gets a temporary, all called ephemeral port number. So this word ephemeral means temporary, or it uses that for the session, and once the web session is over, it's released and then reused. Okay, so what happens now? The web browser has an IP address. This is just a fake address. I just put down some numbers here. And here we know this one. So the web browser now knows its own IP address, and it knows the IP address of the web server, because they got it from DNS. So the first thing to do, the web browser, is do a TCP connection request from an IP address and a port. Okay, so this basically means from the machine that has this IP address and from the software which is talking through port 1127. So this is one of these temporary ports. And then he wants to connect to a machine which has this IP address, and he would like to talk to the software at that machine which is listening to port 80. Question?
Port number 1127, is it related to the NAT part in order to connect to the network outside?
Yeah, no, so this has nothing to do with the network card or the network interface. It's just it's internal to the machine here that randomizes a port number. The software gets this by randomizing this, and it's not really connected to the IP address per se, right? So it's just randomized. This one, port 80, is always the same. So whatever web server we connect to, we know that the web server software will listen to port 80. Any other questions? Okay. And then if the web server is alive and willing to serve another connection, it will acknowledge this TCP request and say OK. So now we have established a connection between the web browser software and the web server software through TCP. Okay. Okay, and TCP is much more complicated than it is more complicated than what I explained here. There are actually several messages going back and forth here before this connection is established. But this is the gist of it. Okay, then the third thing is to request a file. So the web browser requests a file, and they request a file from the server using a protocol called HTTP. Okay, so there is a particular language or syntax associated with this protocol, and that's what's used. So the application, again, applications are addressed used in port numbers. So the web server software listens to port 80, and the web browser uses this ephemeral port number. So what happens now is that the web browser uses the TCP connection, which is now established, and sends a message to the web server software. And it says here, get me this file, and then the file specification, the path of it, using this protocol, HTTP version 1.1. There is a 1.0 version also. So protocols can evolve during time, so there could be different versions of it. And it also specifies the host here. And the reason for specifying the host here again is that this machine can actually have a web server software that hosts many web pages. So it can also host, I don't know, KTH web page. Not that I think so, but anyways, it could be like this. So it has to be specified like this. And then the web server then sends back an acknowledgement that, okay, so using this protocol 200 basically means that everything is fine, and then the data comes to the web server, and then it's displayed. So any questions? No? Okay. So the nice thing about the internet is that it's available. So we can actually do this now. So I showed in slides how to do this. So let's switch over to a terminal on my laptop and actually go through the motions and do it from the command line. This is something that you can play with yourself if you like. Okay, so remember now, what do we need to do the first thing? When the user clicks on www.chalmers.se and then a resource, what is the first thing the web browser needs to do? Yes? Find the IP. Okay, and it uses DNS for this. Now the user program that, okay, so I have some software on this laptop. Everybody has it, more or less. There's several different types of programs that uses DNS to query DNS. And there's NS lookup and so forth. But I use Dig here. Dig is just a software program that uses DNS. And then I ask Dig, I give Dig the domain name or the internet name here, and Dig then uses TCP to interact with the TCP server, which is configured when I open up this laptop and it got its own IP address. Okay, so there is a lot of information here, basically some status messages and so forth, but the important thing here is the answer section. Okay, so it says here that www.chalmers.se, and there is some blah blah which we don't care about, but this one we care about. This is the IP address. So 129.16.71.10. This happens to be the IP address today. Tomorrow it could be some other IP address. Maybe the server has changed its IP address, or the web page has moved to another server. Okay. All right, so number 2 then, what should we do? Now we know the IP address.
Request the connection.
Thank you. So we request a connection now to, and we use TCP for doing this. Again, there is we cannot access TCP directly from the command line like this. There are several programs to do this. I will use Telnet. Okay, and then I would then connect to this. Let's see if I remember the syntax here, but it's 129.16.71.10. I think I need to specify the port here also. Probably in this syntax. Okay, I want to speak to port 80. Hey, success. Right? So now we are connected. Now I'm talking to the web server. And the next thing to do is, I won't torture you and ask what the next thing is. It is to get the web page. Okay? And I do that by using the get command, and now I need to remember exactly the syntax of this. Just 1 second. Yeah, so what I want to do is I want to get /en/pages/default I need to spell correctly, default ASPX, and then I use the protocol. I need to specify what version of the protocol I'm using. Okay, I do this, I press enter, but the whole message is not done yet. I also need to specify which host I would like to talk to, and which is .se, and here I need to specify the port again. It's a little bit clunky, but this is the way it has to be done. Okay, and now everything is ready to be sent. When I press return now, the message is actually transmitted to the web server and interpreted at the web server side. And if everything is okay, I will get the web page back. If I've done something wrong, I will get an error message. So let's see, let's hope. I actually got the web page here. Now it's quite big here, so I need to scroll up here. Okay, so we just did these things, right? And then the return here. And then this is the answer from the web server. It says, okay, you get something here with the HTTP 1.1, 200 means everything is okay. It writes okay here also. And then there's some information, blah, blah, blah. And then at the end here it says, okay, you will get now information which consists of 95,267 bytes. That's the first home, that's the splash screen at www.thomas.se. And then here it comes, it's an HTML document, and there's scripts and stuff, and blah, blah, blah. And I don't know, this is probably a picture of some sort. And then, you know, stuff. And then this would then be interpreted by the web browser software and display a nice picture for the user. Right? So, yeah, you can play around with this, and as long as you don't do anything really stupid, this is quite allowed. It's nothing, you know, as long as you're not trying to mess up the service, you know, denial of service attack or something like this, you can do this for sure, no problem. This is what's done under the hood anyways when you click a link on the web browser. Okay. Any questions? Yes.
Is it a big page or a small page? Considering the bytes?
I don't know. Today these web pages are quite large, but if you look at the actual textual information on the web page, it's huge, right? 95,000 bytes is 95,000 characters. It's a big document. So the early web was very much more compact than what we have today. Today we're spoiled with very high bandwidth connections, large big data rates and so forth. So then but this could be a problem, for instance, where you have limited connectivity. Yeah. Okay, so we've done this now. So let's get into the more theoretical sides. Now we've done an, like a extended example here. But what is actually going on? How do we structure this? What is TCP? What's HTTP? How in what layers are these protocols? How do they interact and so forth? On this example here, we encountered a number of protocols: HTTP, Hypertext Transfer Protocol, DNS, Domain Names System, and TCP Transport Control Protocol. So the question is, how does this relate to layers and services? Because that's what we started with. We have layers. Inside these layers there are protocols. And the purpose of the protocols is to provide services up by using services down in the stack. Okay, so a protocol is a set of rules that determines how two or more communicating entities in the same layer interacts. Okay, so I would like to stress this. So communication between protocol. A protocol determines communication between two pieces of software running in the same layer on two different machines. I will stress this further. If this is unclear, it will come later on. Okay, so messages between these communicating entities are sent and received, and actions taken by these softwares are based on events. For instance, when we send something or when we received something, and what is the meaning of this message. There could also be timers and so forth that creates these events, or user interaction. You know, somebody clicks on a link or something like that, or the operating system needs to do something. Okay, so we have here two machines. We have node A and node B. In node A, there is a protocol stack, and here we have the nth layer. So, I mean, you know, n could be, say, n is equal to 3, say, you know, 4 or 3 or 2 or whatever. And then in this layer, there is a protocol A, sorry about that. Protocol A, there is also a protocol B, there could be a protocol C. There could be many protocols which lives in this layer. But let's concentrate on protocol A. This protocol A talks to another protocol entity in node B. So protocol A sends messages this way and receives messages this way. So there is messages going back and forth here. And these messages are then, the syntax of it is specified by the protocol, the rules of the protocol. So maybe this is HTTP, then these are HTTP messages going back and forth. Okay. So we can think of protocol A here, the entity is a piece of software that's running on a machine, and here's a piece of software running on another machine. And they're exchanging information and changing their behaviors according to these information. And then there could be a protocol B that does the same thing. Could be, for instance, this one might be DNS, and this sending DNS messages back and forth. Any questions? It's pretty straightforward, or? Yeah, okay. Now, the purpose of a protocol, and I would like to stress that also, is to provide a service, and it should provide a service to the layer above it. Let's talk about application layer protocols. An application layer is on the top of the protocol stack. So this is the highest layer, and this is the layer whose services is used by software, user software. So HTTP and DNS, these are application layer software, application layer protocols. So that means that HTTP and DNS, what they do is they provide services to application software. So the web browser is using the services of DNS and HTTP. Okay. So, and to do their job, HTTP and DNS, they use what's known as the transport layer, which is below it. We will talk more about the naming of the layers a little bit later, so don't worry about that at the moment. And it uses the transport layer service in order to provide services to application programs. So we have some software, the browser and the server software, they need to talk to each other. And they use the application layer protocols to do this. So HTTP, for instance, web browser uses HTTP and then sends HTTP messages to the web server software, and then goes back and forth like this. Okay, so provide useful services to the browser and to the server. How is this done then? Well, actually these messages that goes across like this, these are called virtual communication It's virtual communication when it's horizontal like this, because this is logically how messages flow in the system. But physically, these messages are transmitted using the service which is below the application layer here, which is the transport layer. So the message that goes like this actually goes down first to TCP and then is transmitted over to the other side using TCP and then popped up to the application layer here. So we have virtual communication like this and physical communication like this. Questions? Okay. So, of course, TCP is not transmitting these messages by itself. These are virtual connectivity, virtual communication between the TCP entities. It's actually using the layer below it to do this. So data is flowing from the top down to the bottom of the protocol stack, and then it appears at the other side and then goes up through the stack, enabling this virtual communication. So let's take a short quiz here, so I know how you think about this, and maybe you think this is trivial or very difficult. But if we look at the first question here, and the question is, what is true? We have three options. A layer can contain many protocols. A protocol can span many layers. Or three, there is exactly one protocol in each layer. So I'll give you 10 seconds to think about this. One is true and two are wrong. Okay. So how many believes one? Two? And three. Okay. It's actually one which is correct. So a layer can have many protocols. Remember the application layer, it had DNS, HTTP, there is a bunch of layers which all reside in there. But a protocol is never in two layers at the same time. So TCP is a transport layer protocol. It is not in the application layer, has no business there, and it has no business in the network layer which is below it. So it's confined to its own layer. And then number three is actually the complement of number one. So, I mean, there is many protocols in each layer, all doing different things. Okay, so question number two here. So what is true by the application program? So like a web browser, it is a protocol in the application layer. It uses the service of the application layer, or it provides services to the application layer. Again, I'll give you 10 seconds to think about this. So how many believes one? Two? And three. Again, two is correct here. So the application software is using the application layer and it's using its services. We provide services up, we use services down. On top of everything, we have the application layer, and these are protocols that provide services to application software that's running on top of everything. Okay, good. So let's take a 15-minute break.